Hello, and welcome to Epidemiology. Let me ask you a question. What does risk mean to you? What's a risky behavior? If I start smoking, what's my risk of getting lung cancer? If you're a doctor and a patient asks you, how do I decrease my risk of getting heart disease by changing certain behaviors? How do you compute that? How do you turn that into a measurable concept? Well, today we're going to talk about risk and how to measure risk. You're going to learn how to set up a contingency table. That's a kind of way that we use to display our numbers to compute risk. You'll also learn how to calculate what we call relative risk, and also how to calculate relative risk reduction. And also you'll calculate absolute risk reduction, all measurements of risk. So, analytical epidemiology is about discovering and describing relationships between risk factors and outcomes. Risk factors. Remember, a risk factor is an independent variable that may change the probability of getting a certain outcome. So we say that smoking is a risk factor for lung cancer. So sometimes we don't know if a behavior or a risk factor is causal or not. We don't know if it actually causes an outcome. The best we can say is that it's associated with an outcome. Smoking is associated with lung cancer. We assume that it causes lung cancer. It almost doesn't matter if it's causal or not. We can control the outcome by controlling the behavior or the risk factor. So today we're going to explore what this association means. If I say that this risk factor is associated with an outcome, what do you think that means? Well, it means that there is a statistical relationship between the exposure and the outcome. We say that there is a numerical statistical relationship between whether or not you smoke and whether or not you get lung cancer. So, in order to do this, we need to set up what's called a contingency table. We call it a contingency table because the outcome is contingent upon whether or not you get the exposure. Now, pay close attention because the way you set up this table will determine whether or not the formulas that I show you will actually work. It's important to do it this way, where the exposure status is on the horizontal levels of the table and the outcome status is the vertical components of the table. Some textbooks will transpose that information as a way of testing you. So if you're referring to a textbook, make sure that they set up their tables the same way that we're doing it here. Otherwise, the formulas won't work. As well, the positive must be the first thing. For example, whether or not you get the exposure, yes is first, no is second. Yes outcome is first, no outcome is second. It's important that this contingency table looks like your contingency table. Otherwise, the formulas will not work. So, we're going to populate this contingency table with information for people who smoke and get lung cancer, or have a risk factor and get the outcome. We call that A. If you have the exposure and not get the outcome, let's say you're a smoker who doesn't get lung cancer, you're in category B. If you don't smoke and you still get lung cancer, you're category C. And if you don't smoke and you don't get lung cancer, we assume this is the majority of people, that's outcome or category D. And we have a total number of people in our set, that would be N. We call the sums on the ends of our contingency table marginals. So, some important concepts to consider. The first is absolute risk. When we talk about risk, we're talking about incidence. You may recall that incidence is a proportion of new cases that we encounter. If I start smoking, and over some time I get lung cancer, that my experience represents a single incident case because it's new. If I had cancer before I started smoking, it's not incident because it was already there. So the absolute risk is, if you're exposed to a factor, what's the risk that you'll get that outcome? If I'm a smoker, what's the risk that I will get lung cancer? That's the absolute risk. The relative risk, on the other hand, is when I compare the absolute risk of getting the outcome if I'm a smoker to the absolute risk of getting the outcome if I'm not a smoker. To put that in general terms, the risk of the outcome when you're exposed versus the risk of the outcome when you're not exposed. That's relative risk. We're also going to explore, in another lecture, attributable risk. That's when we try to compute how much of my outcome was actually due to the behavior that I care about. How much of the lung cancer was actually due to the smoking and not to other factors. So, absolute risk, again, is a proportion of people with a yes outcome. There are two kinds of absolute risk. There's the absolute risk amongst those who did the behavior, in other words, those who were exposed to the exposure. And again, go back to our contingency table. We give that as A over A plus B. The number of people who got the outcome who smoked divided by all the people who smoked. As opposed to the absolute risk in the unexposed group. That's the number of people who got the outcome, in this case lung cancer, divided by everybody who didn't smoke. Two concepts there. Absolute risk in the exposed group, absolute risk in the unexposed group. Now I'm summarizing it one more time. The cumulative incidence rate amongst the exposed is A over A plus B. Again, that's the risk of getting the outcome if you smoked or had the behavior. Absolute risk in the exposed group. The cumulative incidence rate in the unexposed group is the other side of the argument, C over C plus D. In other words, the risk of getting the outcome, lung cancer, if you didn't smoke. So back to our table again. You see where those numbers come from. Now let's talk about the absolute risk reduction. That's how much my chances of having the outcome changed by not doing the exposure. My chances of getting lung cancer, how much did that reduce or increase when I didn't smoke? So again, the cumulative incidence rate amongst the exposed group, A over A plus B. Again, that's my absolute risk in my exposed group. The absolute risk in the unexposed group, once again, C over C plus D. The difference between the two, that's my absolute risk reduction. How much risk I had from being exposed to smoking minus how much risk I had when I didn't smoke. That difference tells me a lot. It tells me how much I have gained in terms of health by not doing that behavior. Now let's talk about relative risk. Relative risk is the granddaddy of them all. It's what we always care about the most. It's what public health officials really rely upon a lot to make decisions about what kinds of behaviors to tackle. So back to our contingency table again. The relative risk is going to be the proportion of our absolute risk in the exposed group over our absolute risk in the unexposed group. Again, these terms sound very similar. That's why I want you to be very careful and always refer back to the contingency table because that'll help keep it straight in your mind. So again, the cumulative incidence rate in the exposed group. Again, the incidence of getting lung cancer or the outcome if you do the deed, if you do the exposure, if you smoke. That's over A over A plus B. The cumulative incidence rate in the unexposed group, again, the probability of getting the outcome of lung cancer if you don't smoke is C over C plus D. We've covered that already. Those are absolute risks in both categories. If I divide those two, I get a relative risk. The incidence rate in the first group divided by the incidence rate in the second group. Now, you may recall when we talked about cohort designs versus case control designs that we can only compute incidence rate in a cohort design. We can also compute incidence rates in a randomized controlled trial. But in the world of observational study, only in cohort studies can we compute incidence rates. So when I'm talking about relative risks and absolute risks, I'm only talking about cohort studies. Case control studies, we cannot compute relative risks because we cannot compute incidence rates. To do so, to give a sense of risk in a case control scenario, we're going to compute something different called an odds ratio, and we'll tackle that in another lecture. Now, let's talk about an example. Let's say we have a cohort study, and again, a cohort study allows us to compute incidence because a cohort study, as you may recall, begins by ascertaining exposure status and waiting to see if the outcome manifests. Do you remember that? If you don't, I hope you review it. I'll say it again. A cohort study begins by ascertaining exposure status and waiting until the outcome manifests. So this particular cohort study follows 100 smokers and 100 non-smokers over a 10-year period to see which group ends up with more lung cancer. Straightforward, classic observational cohort study. Let's look at their data. So let's set up a contingency table again, exactly the way that we were doing it every step of the way, with our exposure status horizontally and our outcome status vertically. So 75 individuals smoked and got lung cancer. 25 individuals smoked but did not get lung cancer. That constitutes 100 of my smokers. Amongst my non-smokers now, 10 people did not smoke and they still got lung cancer. That's an important consideration, something that the layperson often forgets. It's possible to get the disease, to get the outcome, even if you did everything right, because that's the nature of the world. But in this case, in our hypothetical sample, 10 people didn't smoke and they still got lung cancer. That means that 90 of my 100 non-smokers didn't smoke and did not get lung cancer. Okay? So I add up all my totals in my marginals and I get these numbers. Now my relative risk is going to be the incidence rate in my exposed group divided by the incidence rate in my unexposed group. In other words, the absolute risk in my exposed group divided by the absolute risk in my unexposed group. And I get these numbers, 7.5. Is that big? That's a big number. 7.5 we consider to be a very large relative risk. It means that your risk of getting lung cancer if you smoked is 7.5 times more so than if you didn't smoke. If it had been 1, if the number had been 1, that would mean that the risk is equivalent. And there's nothing to be said for that. Maybe we conclude then that smoking has no relationship with lung cancer, but 7.5 is extraordinarily high. My absolute risk reduction, you may recall, is the difference in those two incidence rates. I subtract them and I get 0.65.
What does that tell me? It tells me that if I didn't smoke, I can reduce my rate of getting lung cancer by 65%, which is extraordinary.
So those two ideas, relative risk and absolute risk reduction, give me two separate nuances of information that together form a comprehensive whole about the power of smoking in causing lung cancer or being associated with lung cancer. Now, there's something called relative risk reduction. This is the proportion of baseline risk that is reduced through non-exposure. What does that mean? It means if I don't smoke, how much less lung cancer can I expect in the population? And it's given by this formula. A relative risk reduction is the absolute risk reduction divided by the incidence rate in the unexposed group. Let's look at an example again. Here's my contingency table. And here we have the same example again. We have 100 smokers, 100 non-smokers being followed for 10 years, and we see again an absolute incidence rate or absolute risk in the exposed group and absolute risk in the unexposed group. Here are my numbers, same as the previous example. Now let's compute my relative risk reduction. That's going to be the absolute risk reduction divided by the incidence rate in the unexposed group. We've done that math already. It's 6.5. What does that mean? It means by avoiding smoking, reduce the relative risk of lung cancer by 650%. So, what have we learned? Now you're able to set up a contingency table for computing measurements of risk, and you're able to compute relative risk. You're also able to compute a relative risk reduction and an absolute risk reduction. Thank you. Hello, and welcome to Epidemiology. You know that smoking's bad for you, right? You know that smoking is probably the most important and prominent risk factor in probably causing lung cancer. But I bet you also know people who have smoked all their lives and lived to be 1,000 without having any appreciable illness. And I bet you also know people who have probably tragically succumbed to cancer and never having smoked a day in their lives. That's because exposures don't necessarily result in a disease outcome. It's just that they're more likely to do so versus people who aren't exposed to those things. So what we care about is how much of an outcome, like lung cancer, can we attribute to an exposure like smoking. So today we're going to talk about attributable risk, and you're going to learn how to calculate two types of attributable risk. We're also going to change tacks a bit and talk about something called an odds ratio, which is another kind of risk measurement. So we've already talked about relative risk. Relative risk is one of the most important measurements of associating a risky behavior or exposure to an outcome like a disease. But now we're going to talk about attributable risk. There are two kinds of attributable risk that we're going to learn about. Now remember, some non-smokers also get lung cancer, and some people who smoke don't get lung cancer. The question is always how much of the behavior can we attribute to the outcome, and how much of the outcome can we attribute to the behavior. That's why we talk about attributable risk, sometimes called excess risk. In other words, how much risk in excess of the baseline does a certain behavior offer? Now, we always go back to our contingency table. Setting up the contingency table is really important when doing the calculations that I'm going to show you. We always have the exposure on the left side and the outcome on the top. The exposure is stratified horizontally, the outcome is stratified vertically, and the positives are always first. Yes, exposure first, yes, outcome first. Keep that in mind, otherwise the formulas that we use won't work out. Now, the reduction in the incidence that would have been observed in the population if it had been unexposed is what we care about compared with the actual exposure pattern. That's a complicated way of explaining this. What we're talking about here is something called the population attributable risk. That's one of the two kinds of attributable risk that we're going to talk about. The PAR is one kind. The PAR is asking, what are the fraction of cases that would not have occurred in a population if, in fact, the behavior had been eliminated? In other words, if people didn't smoke, how many fewer cases of lung cancer would there be? That's the population attributable risk. On the other hand, we have something called the attributable risk in the exposed group. Now, the population attributable risk we often call the PAR. The attributable risk in the exposed group is called the AR. Now, the AR is the difference in the rate of an exposure between the exposed and the unexposed population. I know, it sounds complicated. When we do the math, I think it'll be a little clearer. In other words, the AR is a fraction of how much of an outcome we can say is attributable to a certain exposure. Let's start by examining the attributable risk in the exposed group, or the AR. As always, we begin with our contingency table. You remember how to set that up, right? Exposure is the horizontal components, and the outcome is the vertical components. So the formula for attributable risk in the exposed group is the incidence rate in the exposed group minus the incidence rate in the unexposed group divided by the incidence rate in the exposed group. You remember what those are? I hope, from a previous lecture. Those are the absolute risk values in the various groups. And that's given by A over A plus B minus C over C plus D, divided by our incidence in the exposed group, which again is A over A plus B. Now, you have to believe me when I say that the arithmetic works out magically to the relative risk minus 1 divided by the relative risk. So if you're struggling to remember these formulas, that's probably the easiest way to remember it. Relative risk minus 1 divided by the relative risk is the attributable risk in the exposed group. We'll work through an example in a bit, so just file that away for the moment. Now, the population attributable risk, the PAR, on the other hand, is computed a bit differently. We still use the same contingency table, but with an added nuance, and that is we care about the overall incidence of a disease in our group. The overall incidence is given by everybody who tests positive for the outcome, all the cases of lung cancer, for example, divided by everybody in my sample, or A plus C over N. So the PAR formula is the incidence totally minus the incidence in the unexposed group divided by the total incidence again. Or again, A plus C over N minus C over C plus D divided by A plus C over N. And that gives me a really complicated formula, I know. But let's work through an example, and hopefully this will be a little clearer. So the example I like to always use is the relationship between smoking and lung cancer. So again, a cohort study follows 100 smokers and 100 non-smokers over a 10-year period to see who ends up with lung cancer. Do you remember what a cohort study is? I hope you do. A cohort study moves forward in time. We begin by ascertaining exposure status and waiting to see if the outcome manifests. So in this case, the cohort study begins by ascertaining smoking status and waiting to see if lung cancer manifests. Cohort studies allow us to compute incidence rates. Case control studies do not. Always remember that. That's very important for deciding what kind of risk measurement to compute. So here is, again, our contingency table. We always start with this. And if I populate my contingency table with the data from a study, it looks like this. Again, there's 100 smokers, 100 non-smokers, and they splay out such that 75 of the smokers ended up with lung cancer, 25 of the smokers did not have lung cancer, 10 of the non-smokers had lung cancer, and 90 of the non-smokers did not have lung cancer. Okay, now let's compute our attributable risk numbers. The AR is given by our formula of absolute risk in the exposed group minus absolute risk in the unexposed group divided by absolute risk in the exposed group. And that gives me a final number of 86.7%. What does that mean? That means that 86.7% of the lung cancer cases were probably due to smoking. Because remember, the reason it's not 100% is some of those individuals got cancer without having smoked. That's the nuance that attributable risk purports to offer. Let's compute the PAR now. If we plug in our numbers into our formula, we get a PAR of 0.765, or 76.5%. In other words, 76.5% of lung cancer cases would be prevented in our population sample if nobody smoked. They both purport to offer the same kind of information, but slightly different take on it. So remember to use both of them if you're trying to compute attribution. Okay, now we're going to move on and talk about the odds ratio, which is like a relative risk, but slightly different. You'll probably come across odds ratios a lot when you read medical literature. You probably have already. Remember, when we set up our contingency table, as we always do, a contingency table up to this point has assumed that we can compute incidence rates. What if you can't compute an incidence rate? Remember, relative risks depend on incidence rates. The relative risk is the absolute risk, which is an incidence rate, in the exposed group divided by the absolute risk in the unexposed group. Now, remember, case control studies cannot measure incidence. They cannot. So what do? I can't compute a relative risk for a case control study. We need something to estimate the relative risk. Can you guess what that is? You probably can. It's the odds ratio. We mentioned it already. So the odds ratio can be used to estimate a relative risk, but only when the disease is rare. How do we define rare? There's some debate on that issue, but most people kind of agree that if the prevalence of the disease is about 10%, then the odds ratio can be used to estimate a relative risk. That's the major application of an odds ratio, estimating a relative risk. However, a lot of the more complicated analyses, like a logistic regression analysis, for example, gives us odds ratios for a variety of contexts. So you may encounter odds ratios in a variety of your reading. Don't be afraid of it. It's just a kind of relative risk. It's a kind of way of measuring how much risk does this exposure purport to give versus lack of that exposure. So again, we go back to our contingency table. This is where all the wisdom and all the techniques arise from, making this table correctly. It's important now to remember what odds are. Odds versus probabilities. The odds of something happening is the probability of that thing happening divided by the probability of that thing not happening. So in our contingency table, the odds of the outcome happening are the probability of that outcome happening divided by the probability of it not happening. In other words, A over C. So that's the odds of the exposure in the odds of exposure in the disease group. Now, the odds of the exposure in the undiseased group is given by B over D, following the same kind of logic. The ratio of those two odds is my odds ratio. If I divide those two, I get the odds of exposure amongst the diseased divided by the odds of the exposure amongst the undiseased, or A divided by C, all divided by B divided by D. There's a lot of dividing going on. I can simplify that formula a bit this way. It's just A times D over B times C, the cross products, dividing the cross products. Now, let's work through an example. Let's say we have a case control study using 6 patients with Creutzfeldt-Jakob disease. You may know what Creutzfeldt-Jakob disease is. It's a kind of human mad cow disease, really rare. And we have 10 subjects without Creutzfeldt-Jakob disease. And we want to see how much of that disease was likely due to them having eaten beef, because we think that beef is a risk factor for Creutzfeldt-Jakob disease. Okay, so I start with my contingency table. Let's say that these are my data. Keep in mind, this is hypothetical artificial data. In real life, the data would be quite different from this. If you look carefully, you'll see that I have a total of about, I have 16 patients here, and only 6 of those 16 have Creutzfeldt-Jakob disease. That's a pretty high prevalence. Real Creutzfeldt-Jakob disease is far rarer than this. So this is artificial data. Now let's compute our odds ratio. Odds ratio is going to be the cross products divided over each other. 3 times 6 divided by 3 times 4, or 1.5. What does that mean? It means that the odds of CJD are 50% higher in the group that ate beef. And that lends credence to the idea that beef is a risk factor for Creutzfeldt-Jakob disease. So, some final thoughts on relative risk and odds ratio. When we're dealing with ratios, things divided by themselves, the magic number to think about is 1. If I divide something by itself, I should get 1. If, on the other hand, I get a number bigger than 1, then I know something positive is happening. In other words, the exposure is associated with the outcome. If I get a number less than 1, something negative is happening. In other words, the exposure is protective against the outcome. So how much bigger than 1 or smaller than 1? That depends on your opinion. In general, we like to say that 1.5 or 2 are fairly significant relative risks or odds ratios. If you find numbers of that magnitude or greater, probably something profound is happening with respect to a relationship between the exposure and the outcome. So, what have we learned? We've learned about the major measurements, relative risks and odds ratios. We've learned about what they mean and when to use them. We've learned that relative risks are used in cohort studies and odds ratios in case control studies because relative risks are about incidence rates, and cohort studies can compute incidence rates, but case controls cannot. We've learned about attributable risk, 2 kinds in particular, the population attributable risk and the attributable risk in the exposed group. We've learned in another lecture about relative risk reduction and absolute risk reduction as well. Now you're able to calculate 2 types of attributable risk, the attributable risk in the exposed group and the population attributable risk, and you're also able to calculate an odds ratio, which is what we do when we can't compute a relative risk due to the fact that case control studies can't compute incidence rates. Thank you.